Thank you very much, Sherry, for an introduction. Thank you, everyone, for being here. So as Sherry said, I'm talking today about some simulations we have been carrying out here at the University of São Paulo with some help of our European partners. Those are blade resolved and actuator line CFD simulations of the flow through the NREL 5 megawatt wind turbine, which is the wind turbine that we chose as to be the benchmark for this project. This work has been carried out by two students of mine, Rodolfo Puraca, who is a PhD student, and Lucas Franceschini, who is a postdoc researcher at our department. Both of them are also in the audience, so thank you very much for putting those things together. Okay, so the agenda for the presentation. First, I'm going to talk about some blade result simulations that we used at OpenFOAM to carry out. Basically, what we have been doing so far is using U-runs, more specifically K-omega SST turbulence model to perform those simulations. And I have results about the rotor and about the entire turbine, with sheared wind and everything. So I'm going to show those first, and then I proceed to show some recent results using actuator line approach in Wink 3D, which is a finite difference code developed by researchers at Imperial College London, mostly. And so those are simulations that are more similar to the simulations that Ardeshi just showed to us. Okay, so it's also important to highlight that everything here is ongoing work. So this both things here we are developing inside the HPCWE project. So those results are not final or anything. I'm interested here in showing the current stage of the research. And of course, if you have any criticism, just let us know, and also some advice. But that's not anything here is not final. It's ongoing work, and we are happy to hear any suggestions that you might have. Okay, cool. Starting with the blade resolve simulations. So OpenFOAM, I guess most of the audience knows that's an open source CFD tool that employs a finite volume method to solve general problems. And in this project here, we use it simple solver, okay, for initialization with steady flow and iterative simple, which we call PIMPLE, to solve the unsteady flow. Turbulence model is K-omega SST, as I had mentioned before. Okay, both the two cases that we studied here are first the rotor, which is on the left here. Okay, with a uniform inflow, 10 meters per second. And the second case is a complete wind turbine with nacelle and tower with profile speed, atmospheric boundary layer profile speed with 10 meters per second at 80 meters height. Okay, so I'm going to start with this case first. So for both simulations, we did some initialization first with potential flow, then steady flow, and then to run the actual time resolved simulations, we had fixed the current number to be a little bit less than 1. So the average time step is 2.7 times 10 to the minus 4 seconds, and the set a maximum of 20 pinpoint iterations per time step. Okay. Regarding the mesh for the rotor, we see some pictures here of the mesh topology and level of refinement. The domain is here on the right. So we have a rotor with 150. So we have actually a disc with 150 meters of diameter, and the domain extends 600 meters in the vertical direction, cross stream direction 600 meters as well, and 800 meters on the streamwise direction. Okay, So in these simulations that I'm going to show, we are using rigid blade. We solved the interface between the rotating disk and the fixed domain using the EMI approach, arbitrary mesh interface. Some people also know that as a sliding mesh. And for those simulations, we have a little bit more than 9 million volumes. Okay, some more details about the mesh. We used the SnapX mesh from OpenFOAM to generate that. First cell length is 2 millimeters. We employed the growth rate of 1.2, 6 layers. At the tip, sorry, the Y plus is 400, and we used some wall functions to model the boundary layer here. Okay, so we are more or less here in the terms of resolution and the boundary layer behavior. Okay, so those are the results that we got from this simulation. We have managed to simulate 50 seconds so far. Performance is something that we still need to improve, but we have been using 250 processors in 10 nodes in a cluster here at the University of São Paulo. That took 35 days of simulations, giving also the queuing time. Okay, so the results in terms of the wake, it's very clear that the presence of the momentum deficit and also the stability of the wake, in the sense that 300 meters downstream of the turbine, the structure is still very strong and very clear. Okay. If you look more into the details of the flow close to the blades, it's possible to analyze how the flow interacts with the blades, and this define structures that are formed close to the sections here. Okay, so those are of course the benefits of having a blade resolved simulation. So we can pay more attention to the details of the simulation close to the blades. Of course, they are much more expensive than actuator line approach, but both approaches have their strong points and weak points. Okay, so we see some detachment going on here for the airfoil at 60 meters from the hub. So it's clear, and I think it's expected that the flow is not uniform in terms of behavior along the blade. Okay. In terms of integral results, we are not very far from the prediction in terms of power production. So 3.2 megawatts, 3.3 megawatts in comparison to 3.6 megawatts as predicted by FAST. And in terms of thrust, more or less the same level of difference, 624 kilonewtons compared to 663 kilonewtons. So we see that there is some room for improvement. I'm going to talk about that a little bit later on. There are some vortices being shed in the middle of the blade, as you see here. That's basically due to the problems with mesh resolution that we are working on. But we believe we are in the right way here. Okay, here you see the time plot of the power and the thrust. So it takes some time to stabilize, but then in terms of the value of the power generated, it keeps very stable. The same is observed for thrust. Okay, so going now for simulations of the flow around the turbine. So the domain here is a bit bigger, so 500 meters in the cross-stream direction. Okay, and we mesh the nacelle and also the tower. That increases the number of volumes. So now we have a little bit more than 12 million cells. Using the same approach to model the blades as rigid and AMI sliding mesh. In terms of the characteristics of the rotor mesh, it's pretty much the same as the results that I showed you before. Okay, in terms of the inflow, it's different from the uniform flow that you used in the previous simulations. Now we have a sheared profile. Okay, That's the formula for the profile. So it's a log profile. You consider ground roughness of 0.01 meters. For this simulation, so far have been able to simulate 20 seconds using pretty much the same structure. Okay. Here we see some results of the wake. I pointed out here 2 stations where we plot the velocity profiles. So upstream of the turbine, so the flow is coming from right to the left. Upstream of the profile of the turbine, we see the log profile that we expect, and after the turbine, we see the very complex structure of the wake. Okay, here we can see some more fine details about the flow around the blades in 2 different positions. First, the top of the turbine, and then at the bottom. That's very different in this case here because we have the tower and also we have the sheared inflow. So we see very significant differences in terms of the flow behavior here, much more detachment when the flow, when the blades are on the bottom position. And that is more striking close to the root, closer to the root. So here it's for 40 meters. Okay. And that, of course, has an influence on the performance of the turbine. So for this case here, our power prediction was much worse. We see that the presence here of the tower generated a lot of detachment on the blades, not on the tip only. And we believe that this perturbation of the inflow and the tower also has its burden on the not very adequate mesh resolution that we have on the blade. And we expect that if we improve the mesh, also these results are going to improve as well. Okay, so going to show here some of the improvements that we have been carrying out now. That's ongoing work. So that's the previous mesh that we employed for the simulations that I have just shown. And that's the mesh that we have now, and we are carrying out the simulations. Okay, so we produced the mesh for 1 blade and then replicate for the 3 other blades. And we are sorting out the interface between them, also using the AMI approach from OpenFOAM. Apparently it's working well. The simulations are still running, okay? And the Y plus has been decreased to 180, so almost more than half it. Have 10 layers in the boundary layer, so the mesh resolution was great improved here, particularly close to the blades. So the same was more or less applied to the turbine. Okay, so and besides that, we also have more elements between the tower and the blade sliding interface. We believe that this interaction here was also responsible for not having a great performance of the turbine. And we are using piezo iterative for the unsteady solution. That's also another try that we are giving, not using simple, but the piezo scheme to see if we get better results. Okay, so those simulations are currently running in some different clusters here in Brazil. So I hope that I have results to show you in the next few months about that. Okay, regarding the actuator lines simulations with Wing 3D, first of all, I have to explain what Wing 3D means. This is a code developed by the Imperial College team. The captain of development is Sylvain Lazare. It's an extension from WinCompact 3D for wind energy applications. High order finite differences is the numerical scheme. It employs a Cartesian structured mesh, which provides then great scalability and also great performance. So we have performed 3 different simulations. First with fixed tip speed ratio of a single turbine and 2 turbines side by side. Then a single controlled turbine simulation for different wind speeds. So that's another very nice capability of the code, that it can deal with the control of the wind turbine. And finally, we have some preliminary results of the turbine moving. Here we are interested in simulating the behavior of a floating offshore wind turbine. So far we have been able to prescribe some motions, quite exaggerated ones, but that were good to, those are good to attest the stability of the code and the capability of this new implementation. And I'm going to show those results to you. Okay, so first, some mesh refinement results for fixed speed ratio, tip speed ratio 7.55, and inflow 11.4 meters per second, which is the rated flow speed for this turbine. So we tested different refinement here. You see the influence in the wake definition. But in terms of the power production, we see that this result here, the middle refinement and the third result here, they don't show that large difference. Okay, so the first refinement, yes, there's a significant difference between the power and thrust, but as we get to the second level of refinement, so refinement 1, let's call it like that, we see there is no significant improvement in terms of power production. So of course we have more well-defined wake structures. So if you're interested in that, yes, it's worth going this way, okay, and paying more for that, of course. But if you are interested in power, this level of refinement is good enough. Okay, so we tested then with this level of refinement, what happens if you have those two turbines side by side. Here, that was a quick study to understand if you are to mount those two turbines in a single floating offshore platform, having them side by side would affect their performance. That was the question that we wanted to answer. Okay, so we performed some simulations with co-rotation and counter-rotation with different spacings, 1.5 diameters, 2 diameters, and 3 diameters. And what we observed is that the influence of the one wake into the other from 2 diameters on or larger separations, we don't see significant influence of one turbine on the other in terms of performance and in terms of the wake stability. And it doesn't matter if it's co-rotation or counter-rotation. Okay, so of course there are some differences in the wakes, but in terms of the general behavior from one spacing to the other, there's no large difference. And in terms of the power production as well, we see that for 1.5 diameters, yes, there's a small difference, but for 2 and 3 diameters, this difference is negligible, really. Okay, so this code allowed us to do this type of study very quickly in terms of setup and run. Okay, so the next simulations are simulation with of the flow through an isolated turbine, but with the control acting on that. So that's the general curve of the generator speed and how the controller acts on that. Okay, so we tested different rotor speeds, 6, 8, 11.4, and 14. So 6, 8 are in the region number 2 of the control, so only a speed control. And then 11.4 to 14, you have also pitch control, okay? And we see that the code performs very well in terms of limiting the power to a little bit more than 5 megawatts, which was expected from this turbine model. And the same kind of behavior is observed for the associated variables. The TSR varies accordingly. So we see that TSR decreases here as we go from 6 to 14. Okay, so the last set of results that I want to show are regarding the movement of the platform. So we expected the motion of the platform where the turbine is mounted on. may modify the structure of the wake, and we are interested on that. And because this could favor turbulent structures, shortening the wake, and you are able then to place the turbines closer to each other. Okay. So we have simulated so far heave, surge, and pitch movements, which quite large amplitude, so 4 meters in terms of heave and surge, and pitch of 4 degrees. So this is much more than is observed on the field. Okay. So here is the base case, unperturbed solution, okay, with no motion and no incoming turbulence. So you see the wake definition here. And what happens if you have surge, so going in the direction of the free stream? We see that some large scale turbulent structures form in the wake, and we see that the stability is developed. So we are interested in seeing the stability analysis of that. So that's part of the current work that we are developing with the group from KTH, including Adeshi, who was the previous talker. And in terms of the pitch, so pitch is doing in this direction here, the motion, so it's an angular motion. We also see very interesting wake structures being developed here, and not surprisingly, different on the top than on at the bottom. And in terms of the heave, so this is up and down. Also, some stability is developed, not as strong as we see in the previous cases. So we are this part of an ongoing work, and we're still investigating that further. And the next step is going to bring these amplitudes down to the more reasonable values and see if those kind of stabilities still remain. Okay. So conclusions so far about these moving simulations, we see a lot of vortex pairing. The movement of the turbine does trigger the instabilities, and we are going to use smaller amplitudes for this kind of study. Okay. So that's it that I had to present to you today. I finished acknowledging the support from FAPESP, which has the matching funds for the HPCWE project. And also some of this work here has been developed in collaboration with the Imperial College team, more specifically on the Wing3D use, and also the KTH team who we are collaborating with to study the stability of the wakes of the moving turbines. So thank you very much. I'm happy to take any questions that you might have.
Okay, thanks, Bruno.